Okay, so what is a zero-order reaction? Well, simply said, a zero-order reaction is where the rate of the production of a product is not dependent on the initial concentration of the reactant. So what does this mean? So, for example, if you had 3 different flasks, okay, so you had an experiment. So experiment 1, in experiment 1, you have a concentration, let's say, of a reactant A, and it is 1.5 molar, and you want to get to a product B, okay? And then you had another experiment where you're starting off with initial concentration of A as 2.0 molar, and you had a third reaction, a separate flask, with, let's say, a 0.5 molar concentration of reactant A, and you want to form B. Okay, so since we're dealing about rates, we are thinking about the production of B as a function of time. Say we're measuring the concentration and molarity of B over time. Let's say this is in seconds. Okay. And we find out in our first reaction, our first experiment, that the production of B was we're forming it at 0.3 molar per second. We're forming B at that rate. We run experiment 2 in a different flask where we have initial concentration of A of 2.0 molar, but we find out that the production of B is going at the same rate. The absolute production of B is going to be different for all experiments, but the rate is the same. Again, we're talking about molarity of B over time point. And then we look at experiment 3, a different flask, where we're starting off with a 0.5 molar of A, and we find out that our production of B over time is the same as flasks 1 and 2. So it doesn't matter then. We can now predict that it doesn't matter what concentration of A we have, the production of B will stay at the same rate. So the rate is constant. So this is now the rate law for this reaction. It is a concentration of A to the 0 power. A number to the 0 power is equal to 1, so this simplifies to the rate law for a zero-order reaction to be rate is equal to some kind of constant. And by the way, in this experiment, K is equal to this, right? Because this is the production of B over time point. Okay, so if we want to show this graphically, we can plot this out on the X and Y type of graph. On the y-axis is the concentration of B. On the y-axis is our concentration of A at a certain time, and this down here is time. So I put a table here, and we're going to go ahead and graph this. So again, looking at our first data point, if we're starting off at 2 molar at time 0 for A, for experiment 1, that would be this mark here, okay? And since it's going to be consumed at a constant rate, the graph will look something like this. So that's the graph for the first point. For the second point, starting off with another experiment where we're beginning with 1.5 molar of concentration of A, let's say it's over here, 1.5 molar, and if we graph off the consumption of A at a given time, it's going to look like this. And same thing for the flask where we have starting off with 0.5 molar of A. Okay, as you can see, they all have the same slope. Well, that slope is, that's your rate constant, negative K. Okay, just to make it clear, since the production of B is a constant, the consumption of A is also a constant. Okay, since A is going to B, and we're producing B at 0.3 molar per second, and this is in a 1-to-1 ratio, and we're looking at the experiment, and we know it's zero order with respect to A, then we know that the consumption of A is also going at 0.3 molar per second because of this 1-to-1 relationship here. Okay, but they all have the same slope. Okay, but this is our rate law. So you may ask the question, well, what if we have another reaction where it is, we know that 2 moles of A is needed to make 1 mole of B. How does that change the consumption of A? And how does that relate to the rate of the consumption of A if we know that the rate of production of B is, again, using the same table here? Okay, so if we know the rate of B, what is now the rate of A using this type of reaction? Well, we find out, basically, we know the rate of B. The rate of B is 0.3 molar per second. Looking at our stoichiometric relationship between A and B, we know that for every 1 mole of B, we're going to need 2 molarity of A. So our consumption of A is going to be 0.6 molar per second. Okay? But still, it'll be 0.6 molar per second consumption of A for every single one of these. That does not change, meaning that is a constant for A. So the rate of consumption of A is 0.6 molar per second, no matter what your initial concentration of A is. That still would give you a constant rate, and the rate is equal to K. Okay, so moving on, since we know that this is the graph of a zero-order reaction, concentration of the reactant decreases over time at a constant rate, so it would look like this. And like I said, the slope is equal to negative K. K is our rate constant. Here, the y-intercept is the initial concentration of A. So, to find out the integrated equation for a zero-order reaction, we just use y equals mx plus b, and y is our concentration of A at a certain time point. M is our slope, which is negative K. X is our x-intercept, which is time. And B is the y-intercept, is our initial concentration of A. So this is our integrated rate law equation for a zero-order reaction. Speaking of graphs, if you wanted to graph a zero-order reaction of the rate over time, since rate is a constant, that means K is a constant. That is your rate law for a zero-order reaction. Then the graph is this. If you wanted to figure out the half-life of a zero-order reaction using the integrated rate law, you can derive this expression. So it will be the half-life of a zero-order reaction is the concentration of the initial divided by 2 over K. And this has been derived directly from this equation. I will not do that here for you, but you can figure it out. Obviously, half-life would mean that your concentration of AT is going to be 1/2 of initial rate. So if you plug this value in for A at time t, you will get this expression for T1/2. So, meaning that if you did this, and simplified this expression, you would end up with this. T1/2 is equal to that. So this is how you figure out the half-life of a zero-order reaction. One more thing to mention, looking at this half-life equation, notice that the half-life of a substance is completely directly correlated with the initial amount of the substance itself. So they are definitely correlated and related to each other.